everyone. My name is Rachel Cedillos. I'm part of an organic chemistry research lab under Dr. Claudia Lucero, and we do natural product synthesis. The natural products that we are currently interested in are a group of molecules under the class of secondary metabolites, and they're called lernaic acids. There are 11 lernaic acids, A through K, and these all share similar chemical structures as trialkyl substituted aromatic acids. These molecules were isolated from various strains of bacteria, for example, the Streptomyces strain, which is shown here, and they exhibit biological activity due to phosphodiesterase 5 inhibition. As PDE5 inhibitors, lernaic acids have the potential to act as therapeutic agents that could aid in treatments for several neurodegenerative as well as cardiovascular diseases, such as pulmonary hypertension, schizophrenia, Alzheimer's, etc. Our research lab has already successfully synthesized lernaic acids A, B, and J. My specific project, however, is to complete the first total synthesis of lernaic acid F. So as you can see, here's our current synthetic route that was designed for this particular molecule. We start with a commercially available reagent, 2-iodo-5-methylbenzaldehyde, and then we run numerous reactions to build the different components of our desired product. So this is a 4-step synthesis. Our first step is a Grignard addition reaction. Here we have our Grignard reagent, and HCl acts as a proton source to form the secondary alcohol product. From there, we take that secondary alcohol product, we perform an acid-catalyzed elimination reaction to give the trans double bond. As you can see, these first 2 steps complete the construction of the conjugated sidearm that is also seen in our final product. In addition, these first 2 steps have already been successfully completed. We got 88% for the Grignard addition reaction and 96% for the elimination reaction. This step is the key step in the synthesis. It's a Suzuki cross-coupling reaction. However, before we're able to perform the Suzuki cross-coupling reaction, we first need to synthesize this reagent here. And we're going to do so by using a type of hydroboration reaction, which is just shown down here. I do just want to make a quick note, however, that the organoboron compound that we are using here, 9-BBN, does have a few different ways of representing the structure. So just to clarify for you guys, you may see this a few different ways, but they are all identical or equivalent ways of referring to the same compound. So typically the way that a hydroboration reaction is taught in an organic chemistry course would be using BH3 as the first step, and then hydrogen peroxide as the second step to give the less substituted anti-Markovnikov alcohol product. However, we're not interested in the alcohol product that forms. What we want is the intermediate that forms. Unfortunately, we're not able to isolate that intermediate, so instead what we're going to do is we're going to start the hydroboration reaction, and then once the intermediate forms, in a one-pot manner, we're going to begin to add the rest of the reagents for the Suzuki cross-coupling reaction directly into the same reaction flask. The Suzuki cross-coupling reaction allows us to introduce the 6-carbon side chain on the north end of the molecule. From there, we just need to hydrolyze the ester to the carboxylic acid, and this completes the synthesis for lernaic acid F. So, as I mentioned, the Suzuki cross-coupling reaction is the key step in the synthesis, so I've included a reaction mechanism to show the flow of electrons and demonstrate how our starting material actually gets converted into product. So this is a palladium-catalyzed reaction. Here is our palladium catalyst, tetrakis triphenylphosphine palladium. This is going to lose 2 of those triphenylphosphine groups so that this can now undergo oxidative addition with our aryl halide. We also have sodium hydroxide. So this hydroxide can attack the palladium, which will then kick off the iodine. Similarly, we also have a hydroxide attacking the boron here. And so now this palladium complex with the hydroxide attached can act as a Lewis base that's going to react with our organoboron compound acting as a Lewis acid. And when these 2 react together, we get this kind of compound here. And we have a negative charge on the boron and a positive charge on the oxygen. And this is not a very stable position, so this is what's going to initiate the next step, transmetallation. So this carbon, which is from the R group here, is going to want to move towards the palladium. And this is due to the fact that carbon is closer to the electronegativity value of palladium in comparison to boron. The last step will just be reductive elimination. We're going to lose these 2 groups to regenerate our palladium catalyst, therefore completing our catalytic cycle and also forming our coupled product. So this synthetic pathway is actually not our first or our original synthesis that was designed. Our initial synthetic pathway actually had 6 steps rather than 4 steps. So just to kind of give you an idea of what that looked like, here is our initial synthetic pathway for lernaic acid F. As you can see, these are the same first 2 steps. We already know those work, we decided to stick with those. But then we redesigned the rest of the synthesis after those first 2 steps. Going from a 6-step synthesis to a 4-step synthesis is all already an improvement. Less steps means less time, less materials, and also less waste, so it's overall just much more efficient already. Our initial synthetic pathway did also utilize Sonogashira cross-coupling as a key step, rather than Suzuki cross-coupling as a key step. And I actually spent several months working on optimizing the Sonogashira cross-coupling reaction. So as you can see, I've included some pictures of my reaction setup here. I used a Schlenk tube for this reaction, and if we take a look at some proton NMR data, here is a reaction that I ran, one of my many trials. So here we have our aromatic hydrogens here in the aromatic region. For the rest of these signals, I was able to make my assignments primarily by using splitting patterns, which is the number of neighboring protons, and using the n+1 rule, and then also by using integration, which are these values down here, and represent the number of equivalent protons. And with all of my signals labeled, you can clearly see that it was in fact able to form products. However, my yields were extremely low, and after several trials with consistently low yields, this is what prompted an investigation into a new synthesis and led us to our current pathway. So the Suzuki cross-coupling reaction and the Sonogashira cross-coupling reaction are very similar reactions, and therefore I can use some of the insight that I gained during that troubleshooting process for Sonogashira, and I can now apply it to Suzuki. So for example, we were originally using bromobenzene, and then when we switched to iodobenzene, we found that iodobenzene worked much better. And iodobenzene is more reactive in comparison to bromobenzene, but to compensate for bromobenzene being less reactive, we were heating the reaction. But that still just wasn't quite enough, and overall, iodobenzene produced much better results, so we decided to switch the starting material for our whole synthesis to now have this iodo group rather than the bromo group. An additional attractive feature of this new synthetic pathway is the removal of carbonylation steps. So my lab mate, Kyle Peterson, who was working on synthesizing linoleic acids B and D, had to utilize carbonylation steps in his synthesis. And this was a very picky and very limited approach that was applicable only to allylic alcohols. However, on the contrary, the method of using Suzuki cross-coupling is a more universal approach that can be applied to all of the linoleic acids as well. So if we take a look at the structures for the rest of the linoleic acids, as a reminder, the Suzuki method allows us to introduce the carbon chain on top, and all of these chains on top aren't exactly the same. You can see that some of these chains are longer, some are shorter, some of them have a double bond, some of them don't have a double bond, and despite these slight variances between the chains, this method can still be applied to all of them, with only slight changes to the synthesis overall. So although my current project is on linoleic acid F, future work entails synthesizing the rest of these molecules as well. But back to my current project, with this new synthesis, I am confident that it will produce the first total synthesis of linoleic acid F. So I just want to finish off with some acknowledgements really quick. I firstly want to thank my amazing research advisor, Dr. Lucero, for everything that she's done for me, mostly just for always supporting me. I also want to thank my former and current lab members, Brandon, Jay, and Kyle. I've included a picture of us here. This is the Lucero group just from over the summer. And I also want to thank Ryan Graves, who is not in the Lucero group, but is a grad student here that has been an amazing peer and friend while I've been doing research. I also want to thank the chemistry department here at Sac State and all of the members of faculty and staff that has been involved. Lastly, I want to thank the Science Educational Equity Program. I was selected as a recipient to participate in the IRA Research Scholar Program, which allowed for financial support for my project. And then also, if anyone is interested, I do have a QR code here. So if you scan that, that will take you directly to the Lucero Group website and kind of provide you with some additional information about what it is we do. And you can also find the paper that was published on the syntheses for linoleic acids A, B, and J. But thank you so much for taking the time to listen to me today. Please let me know if you have any questions. Thank you.
Okay, we have time for a few questions.
Yes.
Where is linoleic acid? Like, what do you plan to use that for?
So if we go back to my first slide. So linoleic acids, they act as PDE5 inhibitors, and as they're also called secondary metabolites, it's like the type of natural products, and these possess like anti-tumor, anti-cancer, anti-parasitic properties. And so what I specifically focused on was neurodegenerative diseases and cardiovascular diseases. So these would be applicable for the pharmaceutical industry to aid in treatments for several diseases. And I think the ones that I mentioned were schizophrenia, Alzheimer's, and pulmonary hypertension. Those are just some of the few, but it could also potentially
so, when you were doing your Sonogashira reaction, and you showed us a really nice NMR there, but you also said that your yield was really low.
Correct.
So, presumably that means you did a bunch of purification before you did the NMR?
Correct.
Okay. So I guess the side question to that is, have you made any effort to figure out what you were making, like what the side products are, right?
Oh, I see, yes.
Yeah.
So, I think the biggest issue that we were having was lack of reactivity.
Okay.
And so I mentioned we were originally using bromobenzene and then we switched to iodobenzene.
Mhm.
The yields increased much more, but we're not really seeing any byproducts other than what would be normal for the reaction. But it was really just an issue with our starting material not actually reacting and not forming product.
Okay, that makes sense.
The other ones, the A, B, J, or B, the other ones that have been synthesized, was that all using the Sonogashira coupling?
No, so that was actually a completely, well not completely, but a different synthesis. So kind of on theme, these are all organometallic reactions. So the key step in those syntheses were something called a Heck reaction. It was actually the same first two steps, but the Heck reaction was the key step for that.
And then now that you changed to the Suzuki cross coupling, what type of yield or NMR result would you feel comfortable with? As you know, before you had such a yield, low yield that you were happy. What would make you happy?
Well, literature is reporting yields of like around 90%. So if we're following procedures from literature, I think that would be a pretty good indicator that we're following it correctly. So I think 90% should be a pretty good range for yield.
Okay. If there are no other questions, then let's move on.